See, we have our speakers, and I have the pleasure of introducing them. My name is Eric Eberhardt. I'm the Director of Energy Services at University of California Office of the President. It's the central office of the UC system, so I get to work with all the campuses, which is great. And I've been working with Anna and Gabe for some time, but specifically Anna since I started more than, I think, 12 years ago. So this is pretty cool. I'm excited to hear more, but we really appreciate Anna kicking us off. But I'm going to do a quick intro with a little background. Anna is a licensed mechanical engineer in the state of California with more than 20 years of experience in energy efficiency engineering and energy program management. And she's currently the Director of Energy, Utilities, and Sustainability at UCSF Health and Technical Director of Sustainability at UCSF Campus. And Anna manages the $42 million annual utilities budget, utilities planning, energy and water efficiency, and building automation programs, all with a focus on developing and implementing technical and engineering solutions to support UC and UCSF's carbon reduction and clean energy goals. So thank you, Anna. And she's with Gabe today, who, again, I've been working with Gabe for some time. Gabe is an innovative controls and commissioning engineer with more than 20 years of experience driving efficiency and sustainability in mission critical environments. At UCSF Health, Gabe manages complex automation systems across multiple hospitals and medical facilities, ensuring uninterrupted support for patient care, all while reducing energy consumption. So thank you again, Ann and Gabe, for joining us and kicking us off as our keynote speakers. And I'll turn it over to you.
Thanks, Eric, for the intro. Thumbs up if everyone can hear me okay. Just to make sure. Looks like it. Okay, great. Yeah, thanks for the intro. It's nice to see a lot of familiar faces and names in here. As Eric mentioned, I've been with the UC system since 2009 at UCSD and then UCSD Health and now at UCSF Health and Campus. So really happy to be here with various colleagues, familiar and unfamiliar. So just to jump in, we're going to give an overview of what UCSF is up to relative to energy and decarbonization. I would say that relative to some of the UCs, we're somewhat early in our journey. Campus a bit ahead of health, I would say, but starting to make some real moves and excited to share them with you today. Gabe's going to do a bit of a deep dive into how we're trying to tee up our technology, our building automation systems, to really be ready for the sort of building optimization and software and AI revolution that is upon us. So look forward to that piece as well. So I wanted to just start with a little bit of a sort of grounding reminder of why we're all here. Those of you who are in or near the Bay Area or Northern California may recognize the scene in the background of the effect of the orange sky back in September of 2020 during the Northwest wildfires. It was certainly very impactful for me to actually physically feel that and see that right in our own home. So Rebecca Solnit, thinker and author, reminds us that the stories of climate change manifest in impacts in this village, that farm, that city, this home, that stream, this forest, that person who dies defending the forest, that person who flees the destruction of the forest and its defenders, that woman who gives birth too soon. And in particular, that last piece for us is particularly relevant as UCSF because we are an academic research and also patient care institution that's really entirely focused on health. So we see this decarbonization effort really as central to our mission. So I wanted to just remind us all, because I always find it helpful to remember what is the very, very, very big picture that's happening. So what you see on the screen is global greenhouse gases per capita. The world overall is there in purple. So you can see the overall trend. The United States is reducing per capita, and you can see a pretty significant drop in 2020 with the start of COVID. But of course, certain neighbors, you can see the increase in China over time. So a major effort. This next one is an absolute, so not per capita, but overall absolute. So you can see global greenhouse gases continuing to climb worldwide, while the United States is flat or dropping somewhat. Meanwhile, in California, we continue to be a leader. The our governor is invested in sort of the worldwide engagement and discussions, and you can see that it's reflected in our continued reduction of greenhouse gases. I would say that not only is California a leader, but also UC, while our actions may sometimes feel small, and certainly they do to me on some days, it's important to remember that we are leading and providing real examples of project execution to the rest of California and thereby the rest of the country. So it's just helpful to keep that in mind as we go forward. I would be remiss in not, I think, mentioning in a keynote at an energy managers conference the intersection of AI and energy. It's all over the news. It's talk of the town, both from, I think, very different perspectives, with some overlap. One being that AI is a massive opportunity, and could really make an incredible difference in, increasing energy efficiency. At the same time, it's being leveraged to increase the, finding and excavation of fossil fuels, and also the data centers themselves. There's significant fear about how much energy use they're going to use. So I just wanted to talk about this a little bit. That Amory Lovins, founder of Rocky Mountain Institute, has pointed out in an essay that the power sector has done naive overforecasting and overbuilding before, and he's a little concerned that that's what's happening today. When the internet boom happened in the 90s, there was a similar level of excitement about the massive increase in load, and he sort of sees similar patterns happening today. It didn't play out the way the fears anticipated. Here, there is significant concern that there's going to be investment and fast investment in more fossil fuel power infrastructure to serve these data centers. At the same time, I think most folks in this room know that renewables are profitable and could be serving these loads, and are in many instances serving this load. So I thought it was interesting to bring forward what Emory Levin said, that he anticipates that vastly more renewables will be built than AI actually requires, no matter how much that turns out to be, because they're needed, profitable, and beneficial regardless. And he points out that if risks are properly managed, the huge uncertainty of demand for AI and for electricity to run it is thus acceptable, because the less power AI needs, the more clean power will be available for other uses, both displacing legacy generators and decarbonization, for mobility and heat sectors. So that's one of his rare optimistic views on AI, but I would say that there is significant opportunity for us to utilize these technologies, and an opportunity for us as energy managers to voice the ability to source renewable electricity for these loads. So getting a little more close to home, focusing on our own university, UCSF, as I mentioned, we're exclusively focused on health. We now, as of the last year, have 6 major campuses in the Bay Area, all of those with hospitals. And 3 of those actually, 2 in the city of San Francisco, formerly called St. Mary's and St. Francis, now called Hyde and Stanion, and also Benioff Children's Hospital, Oakland, came under our purview just in the last year. So significant activity and growth. We see 45,000 hospital admissions a year and 1.7 million outpatient visits a year. We have 36,000 plus employees and 3,000 students, and we have now 12 million square feet of owned facilities. Of that, about 15% is new to us. For those of you who are not in healthcare or in the health space, it's important to know that there's a major 2030 seismic compliance deadline that we're subject to. So inpatients are not allowed to be in non-seismically compliance after the year 2030. Also, interestingly, until the year 2020, hospitals were exempt from the California Energy Code. They actually had been included when it was originally created long, long ago, and then they were made exempt for decades and sort of given a free pass. There's a lot of opportunity and low-hanging fruit relative to our non-hospital facilities. At UCSF, our campus side has had consistent investment in infrastructure renewal from year to year. Meanwhile, on the health side, not so much. We're still working on building up a permanently funded program. So to talk a little bit about the backdrop that we're working with relative to our decarbonization aspirations. On the left there, as with really anyone around these days, but particularly in the academic space and healthcare space, we have rising costs and risk to our funding. So risk to our federal funding, rising healthcare costs. We did have recent layoffs. And we have significant capital obligations in the form of the seismic compliance. We also have housing commitments that we've made. So decarbonization is one of many major capital obligations. We have a growth mindset. So I've mentioned we have additional new campuses. We also have 2 new hospitals in construction, as well as a research building in construction. And also with that growth mindset comes a lot of uncertainty about what the future of our existing older buildings will be. So we're doing planning and thinking about where we're going to go, but also having to be very flexible and nimble because there's not total certainty about which buildings will remain into the future. Meanwhile, on the right-hand side, we are committed along with the UC system to meet our policy of becoming decarbonized by the year 2045. That's 90% below our 2019 baseline. The numbers you see here are interim targets that are under review at this point now that we have newly acquired facilities and the current financial environment. But this is what's driving our decarb conversations. The graph you see on the screen is historical UCSF greenhouse gas emissions. So you'll see in the legend, this includes Scope 1, Scopes 2, and Scopes 3. And then you can see in orange that 2045 goal. Just a note that this excludes those newly acquired facilities. And that light blue Scope 1, very large piece, really the biggest single emitter that is a part of that piece of the graph is our gas-fired cogeneration plant at our Parnassus campus. So that plant is both our greatest challenge and our greatest opportunity from a decarb perspective. It provides some pretty wonderful electrical resilience and serves a steam network that would need to be replaced. So we're not as far along as some of our other UCs in advancing that, but we're taking a very careful look at how we can transition from that steam distribution network to an electrified heat recovery chiller-based system. And across the board for our hospitals, our decarbonization plan includes maintaining natural gas boilers for heating backup that would basically almost never run as a way to be able to have heating backup without having massive diesel generators that are sized to serve the electric heating loads. This is a map that shows most of our various locations. So the overall goal of our decarbonization plan is to switch from natural gas to clean electricity across our UCSF sites. You can see that one of our greatest challenges is that we're all over the place and we got lots of campuses. It's not just 1 or 2 major systems, it's systems across the board. So we do have an intent to invest $300 million in the next 10 years. This is not yet funded or financed, and it's technically only a small portion of the overall estimated $1.8 billion that it'll take to decarbonize. But we're keeping our eye on the ball. Our senior vice chancellor of finance and administration just yesterday said to keep the ball rolling even amidst everything else. And so we're continuing to find and move forward on opportunities where we can. For the sites beyond Parnassus that don't have cogeneration, the overall intent is to have heat recovery chillers and creative ways to both absorb and reject heat to keep those balanced, possible thermal energy storage, and then to supplement heating air source heat pumps for the most part. We are doing some exploration of geothermal potential at our MLK building. And the decarbonization study that we did last year did identify a potential in Oakland for recovering municipal sewer heat through heat pumps. So that's a consideration for the fire partnership with the city of Oakland. This slide here shows what we're up to on our new construction. So this is the area where I would say we have made the most amount of leaps forward in the last year and ongoing. So what you see in front of you, and this is really for the engineers who want to get into the details here, the first two rows are outpatient surgery centers that have been built and are in operation. So the first is Bayfront Medical Building, the second is the Peninsula Outpatient Center. Both are all electric, fully carbon free. And I would say one is running very well and the other we are continuing to work on. The design is pretty much based around heat recovery chillers, and then each of them has what we refer to as a heat sink source coil in the exhaust airstream of the main air handlers. When the heating and cooling are not balanced, that coil can either reject heat by running heating hot water through it to the exhaust airstream, or it can absorb heat by running chilled water through it from the exhaust airstream. And neither of those buildings has cooling towers. And we have actually found that the balancing works quite well. We've run through some heat waves with the Bayfront Medical Building and operated successfully. I would say significant props to the commissioning agent for that building, for Gabe Sandoval and other members of our teams for really making sure that that building was set up to be successful from the start. The commissioning agent was very, very engaged and really looking into proactively finding issues and getting to the bottom of them before they became bigger. That is evident in the last two columns. You can see the EUI target and then the EUI to date. I know we're higher than our target, but relative to what's going on in that building, I'd say we're performing quite well. And also those targets are, they can be all over the map. You'll notice in the newer building, Peninsula Outpatient Center, we are operating far, far, far shockingly above the EUI target. I'm optimistic that with a very careful, focused effort, we're going to get that number way down, but it's a definite focus of ours. The last row that you see in the table is our new hospital, one of the two hospitals in construction in Oakland, also to be all electric and carbon free. Also centered around heat pumps for heating and cooling. That's going to have currently planned to have a modular chiller that can both absorb and reject heat to the air with traditional water source chillers as well, and air source heat pumps to supplement the heating. In all of these cases, we'll have point of use electric steam generation for the relatively small steam loads. And then we've got a couple additional buildings here, a research and academic building on the campus in Parnassus, BRAB we call it, which has heat recovery chiller and also will be tied into the campus chill water loop. That's in construction. And then a major construction project in Parnassus, and that's what this picture on the right is showing, the incredibly high cranes, is building our Helen Diller Hospital in Parnassus, which also has heat recovery chillers. Interestingly, one of the pieces of this to balance out those heating and cooling loads is the plan is to connect the chill water to a neighboring existing hospital so that we can absorb heat from that hospital as needed to help balance those loads. There is still going to be steam use from our gas cogeneration plant for that building, but the long-term intent would be to eventually decarbonize that. And then in terms of non-new construction, but existing facilities decarbonization projects in motion, our Mission Bay campus is getting ready to install a heat recovery chiller in a building called Rock Hall that is funded with campus capital funds and will displace about 83% of the building's reliance on natural gas for heating. And then we are initiating a study at our Mission Bay Hospital to install a heat recovery chiller and an electric steam boiler that we anticipate will displace at least 30% of that hospital's reliance on natural gas. We also have a significant energy efficiency program that's ongoing. We've got $70 million approximately between the two campuses, which does include some decarbonization. And we're looking at combining that with capital funds to try to leverage it as far as possible. So we're really focused on teeing us up for future decarbonization and then doing what we can today. So some of the key things we're doing to tee us up are partnering with our campus planning department and our real estate to ensure that all major pieces, utility lines, thermal energy storage tanks are top of mind as early as possible. And they've been very interested and engaged in talking to us about where potential locations could be for those. There's a lot of need for increased parking on our campus, and there may be some opportunities to partner with parking garage projects. We're also working with design and construction to ensure that key pieces are included in all renovation projects. So, anytime we do construction in a hospital, it's incredibly disruptive because we're trying to do patient care 24/7. And so anywhere we're able to just include the advancement of decarbonization in an existing renovation project, we're making sure that's happening. So removing any steam dependence, making sure that heating hot water coils are sized for low temp heating hot water, and making sure that our building management system specifications are heated. And then the last piece we're really focused on is really teeing us up for taking full advantage of current and future building optimization technology like AI. So, there's a lot coming and there's a lot coming fast, and we want to make sure that our physical software and hardware is set up in such a way that we'll be able to really take advantage of that. And I'm gonna pass the mic to Gabe here to do a deeper dive on that particular topic.
Thank you, everybody, for joining this meeting. Hopefully, I can keep you guys interested, as Anna did. She did a really good job. So, yeah, and primarily, I'm going to be focusing in on leveraging technology for energy and decarbonization. That is my focus. Those that know me, I've been working in building automation for many years now, and I'm very focused in on exploring and using the latest technologies for trying to reduce energy and help with decarbonization. As I was presenting or preparing for this presentation, I was thinking back to the times that I spent. I used to work at UCSF some years ago, and I had the privilege of working with Patrick Testoni there, the energy manager. We did a lot of really, really great work there. We played a lot of basketball, but we also did some great work together as well. One of the things that we were actively doing at that time is we were using, they had the PG&E program at the time to save energy. Was a pretty open and active program. And so Patrick and I, we did a lot of projects together. One of the things, though, that we had learned from doing those projects is what would usually the process would be is Patrick would pick a building. I would go through, and we did a lot of the work in-house. We would go through, replace all the building automation. And so usually what Patrick would tell me to do is we would just mimic the sequence of operations that are existing. Don't change anything. We won't do any measures, no optimization programming. Just copy what's there, implement it, and then we'll commission it. And then afterward, we'll do some benchmarking from that, and then we'll do energy optimization programming later. And it was an interesting process because what we found is every time we would go through and just replace the controls, maintain existing sequences, we would always wind up still saving energy. We would save 10, 15, 20%. And it was a consistent metric that we kept finding with every project that we did. I think what I took from that, though, is I learned that using the latest technology matters. It helps with reducing energy. There's reasons behind that. We won't dive too much into it. Better visibility, just better controls, faster, easier to program, easier to access. There's a lot of reasons behind that. But technology matters. It matters going from all the way from the bottom, lower level sensors, all the way up to top level software. And that lesson has always driven me since that time to continue to just focus in on that as I'm working on these systems, is trying to leverage the best technology for trying to help reduce energy and help with decarbonization. For this particular subject, for dealing with what we're dealing with here at UCSF, one of the things, the challenges that I find, and I think probably many people find, is implementing some of the current optimization recommendations that are given, primarily with guideline 36. And I'll reference that as part of this because guideline 36 contains instructions that I think focus on really the three primary areas of controls and trying to reduce energy and help in the buildings. It deals with operational controls, so how you control air handlers, opening dampers, closing, things like that, opening valves. It deals with an optimization layer, the supervisory control, the resets, apply your temp resets, pressure resets, things like that. And then the intelligence layer, the fault diagnostic detection. If you read into that guideline 36, it tells you to deploy, it really gives guidance to deploy it within the building automation system. Which is interesting because to me, that presented a lot of challenges that I think we're all facing in trying to deploy these things, these optimization, particularly the optimization part of that in the control systems. And even if you go back and read the initial report that they gave when they released Guideline 36, it even referenced some of these challenges that they recognize. One is you need a modern BAS system. And even within that, if you really dig into some of the various control systems, many of them struggle. I often complain about this, that we have control systems that still are using technology that's 40 years old software to program their systems. So if you're trying to implement these new latest advanced sequences, it becomes a real struggle. If you dealing with the different customizations of each buildings, I think Anna referenced some of our projects that we did recently. These all-electric plants are really complicated. The sequences that we're dealing with now are pages of sequences. I found this to be one of our most challenging areas when trying to implement this type of advanced sequencing. Contractor capabilities, again, oftentimes a lot of these contractors, their programmers are new, they're unfamiliar with HVAC mechanical, and they're trying to implement these recommendations, and it becomes again another challenge. And then just operator training, and trying to get them to understand these resets, how they work, how do you attune them, how do you adjust them. I think all these things again present challenges to maintaining and implementing them. And then again, this guideline was initially released 2018. I think they did an update in 2021. But even since that time, technologies have evolved. So does it still make sense? Again, the way that they're recommending to implement it, the way that we're trying to maintain it, does it make sense to continue to deploy it within the building automation system? Again, I'm going to take a little bit of a deep dive here. Hopefully you'll stay interested in this. If you kind of look at, I created this just basic architecture of what I term as a legacy BMS architecture. I call it legacy because this is when we were still using, we don't use this type of design anymore, but some facilities still do. But you would have like the BMS front end that connects usually through an IP or Ethernet down to network controllers. And then these network controllers would then integrate all these serially connected VAVs and air handlers. Again, thinking about implementing Guideline 36, if you broke down the different functions or the different logic that would be deployed, it could be deployed across these various controllers. The operation control and fault diagnostic detection could, oftentimes you might see it in the VAV. In the air handlers, you would also see the resets running in, as well as the basic operation control and even some fault diagnostic detection. And then you can see all that programming might also exist in the network controllers as well. So as you go through these systems, you kind of have to search through and find where they put this logic. oftentimes through the project, we would try to make the decision where we would locate these different functions. The challenges that present is that these aren't one-to-one matching architecture. So you might have an air handler that has VAVs that the air handler serves that might exist across different network controllers. So when you go to start mapping all this out, what it begins to look like is something like this, where you have to map up through the network controllers, pass data between the network controllers, down to the air handler, back up through the network controllers, and then eventually this all gets integrated up into the BMS. This is a very common setup and program that you'll find. Again, very challenging when you're trying to maintain this and trying to keep it going and making sure it works, commissioning it, it becomes a very challenging architecture to maintain. The way, if you look at modern controls, I call it a more modern type of control system. This is what we're implementing here at UCSF, and I think a lot of sites are now gone to this, where we are deploying IP-based control systems. So we no longer deploy that middle layer of network control. We don't find that as a needed item anymore. So all the VAVs, air handlers, or any other plant equipment or HVAC equipment gets connected right directly to the BMS front end. It is a much simpler way to deploy it. It has taken out a lot of the complexity. If we go to, again, thinking about that guideline 36 and what it recommends, a lot of that logic then gets pushed down directly into the BMS system. And then when you start, again, focusing on, if you had a similar situation where you had VAVs that would go to one air handler, other VAVs going to another, again, the mapping becomes a little bit simpler. It still can become complicated though. Like in the case of, like Anna mentioned, Bayfront, we have 6 air handlers. You may have 50 to 100 VAVs being mapped to each air handler. Did this make it much easier to deploy Guideline 36? In my opinion, it didn't. I think from these projects, looking back at them and talking with the BMS contractor and kind of looking how they deployed these different aspects, it still wound up being very complicated. In this illustration, I only show 4 VAVs. Again, oftentimes it's 50 to 100. That mapping becomes a very complicated process, and it's an easy breakpoint for these systems. The logic that winds up living in these air handlers, if you look at it, it becomes really, really complicated to kind of work through. Again, better than what it was, but I still didn't find it ideal to maintain long term. And thinking about that though, as I was looking at this project and talking with ones at it about it, when you start thinking about, again, Guideline 36, what you find is that it really, again, it breaks down to the 3 different areas, right? The supervisory control, optimization, operation control, just basic running the equipment, and then the fault diagnostic detection. I think most of the UCs here have gotten pretty advanced in that, we've taken out that fault diagnostic detection. I think most of us use SkySpark as our FDD. I think it works, way better than putting it in the BMS, because, you're dealing with trended data. Oftentimes in the BMS, you don't deal with trended data. So I think that has been a vast improvement. What about this optimization though? I think that's the one area that I think is interesting to me to think about. If you were to think of this as a single controller, and again, this is just a very simple diagram. I simplified it. I know it's much more complicated. But what usually is happening is you're passing data, even within a controller, you're passing data from a VAV or an air handler. It gets pushed up into the operation logic. The operation logic then runs its logic, makes a decision for a reset, and that gets pushed down back into set points like supplier temp set point and supplier pressure set point and a few other ones. But it really is logic that can be separated out. It doesn't need to exist within the same controller. And I think understanding that helps you to be able to determine, is this the best way that we can deploy and maintain this logic? some years ago, well, I'm going to add one more thing, and then as well as you have the analytics logic as well. And again, like I said, I think we've got a good way path forward on that. Some years ago, I was working for a short time. I went to go work for Stanford University, and they began to run a project called the Stanford University Cooler Project, and it was a project we were working with a group of PhD students that were doing research on energy and buildings. And this was back, I think, in probably 2019 it started. And one of the things that they wanted to do is at Stanford, at that particular time, they're having issues with some of these heat waves. The main plant wasn't capable enough at that time to produce enough chill water. We had to go through curtailment periods and shut water down for certain buildings and adjust set points and so on and so forth. So they approached this group about doing studies on the buildings and trying to model out the cooling demand, and if there's a way that we could predict be able to predict how much cooling a building will use under any given set of circumstances and temperatures. And if we made adjustments to set points throughout the building, how can we affect the cooling that these buildings use? It was kind of a fascinating study that they did. But when I sat down to talk to them, we started talking about, just asking questions of what exactly do they need to do this study. So they had a Python. They wanted to run these models within Python. They had a database. I don't know what they used I don't know if they used SQL underneath it or what, but they wanted our trended data. So, we had our BMS controllers. Most of it was serial connected to network controllers where we had our trends. And so I had the challenge of, well, how was I going to give them this trended data to support their research? So one of the things that we had started doing, though, is we began to use SkySpark. We deployed it started deploying it site-wide throughout the university. I had the idea of, well, could we supply that data from SkySpark? And so I knew there was something called PyHaystack. So they made a connection to SkySpark and they started pulling trends through that database. But then they wanted to find a way to then make set point changes. So they asked us, they said, well, can you make set point changes daily, right, throughout the day? And at that time, I was managing the group of about 6 or 7 engineers, and anyway, the thought of like having a person every day go make all these set point changes and the amount of time and effort, it just didn't seem like a real productive time. But I wanted to support this project. So one of the things that I knew that could be done is we could actually write back through SkySpark. And so we worked with them on this. We set up some limitations. This was during, I think, 2020 that they began this process. So a lot of the buildings became empty due to the pandemic. So we got permission to actually run these tests on these buildings to go through and make set point changes and throughout the day and adjust set points, cooling set points and heating set points and so on and so forth. So I worked with their team, created the way that they can do that, tested it, and it worked really well for their project. But as we went through this project, it got me really to think about that idea of here this team was able to do this advanced data analysis, this modeling of data, make decisions, and then write back into our set points. Which again, if you think about guideline 36, that is in essence what we're doing, right? We're making these advanced we have this advanced logic. We're doing this optimization logic, making decisions, and then writing back to our operation control. So it got me to think about this, like how is there a way that we can do that, something similar, but essentially do it on every building, and be able to improve our set point control, not having that logic just run in our building automation controllers, but do it more on an advanced level. And then even think about doing that more towards looking at more advanced optimization, even predictive model, because again, we're dealing with trended data and they can do this type of analysis. So as that happened, it got me to start thinking about that. So again, if you think about this, our modern BMS architecture, how would we deploy something like that? So one of the things that I got to thinking about is using SkySpark. SkySpark, I know, is a very common software that is used. It is capable of running live control and making these type of decisions. And so this is one of the things that we are actively looking at here at UCSF to do for not just for our existing buildings, but for our new construction projects as well. I was pleasantly surprised. I was talking to LBNL recently and heard that they had already started doing it. They're doing it on a VM level, and it sounds like they're having a lot of success doing this. But again, thinking forward, thinking about the idea, does it make sense to have this in our local BMS? I'm pushing for it to be that it doesn't, that I think we maintain our operational control within our local controllers. We push the more advanced controllers up to something like SkySpark, running it either in a locally like industrial PC or possibly on a VM. And I think both of those things I want to further test out. But I think one of the things it does is it gives us an opportunity to be able to test out, different optimization programs. One of the challenges we have at healthcare, and I think Anna mentioned it, is with a lot of these live buildings, we can't just go through and download new programs within the air handler controllers to run new optimization. Those things we have to kind of go through an approval process, plus they're 24/7 buildings. I think by segmenting it out, it gives us an opportunity to deploy it without affecting the operation of the buildings. The one other thing I think too, it gives us the opportunity is if we're looking forward to, like Anna mentions, is some of this advanced machine learning, AI, whatever we want to term it, that it gives us an opportunity to be able to deploy that within buildings if this is segmented off our our BMS system. Again, thinking about those implementation challenges, does it help with these things? I think it does. I think it alleviates some of the technology requirements that the BAS needs by segmenting it out onto a different system. It allows us to have more to templatize the optimization, because if you're using a single software, you no longer have to adjust it for each particular building automation system you may have in the buildings. It takes off that complexity of implementation from the control contractor. They no longer become responsible for deploying that. And then I think, again, it alleviates the operators from having to maintain that particular software. That's all the time I have. I'm going to turn it back over to Anna.
All right. So for some of you, that was probably a highly welcome deep dive, and you were eager to look at the BMS network architecture. And for others, maybe deeper than anticipated. But to me, the big picture takeaway from all this is building optimization work is moving very quickly. ASHRAE guideline 36 is one, but there will be a 37, a 38, 39, but really there will be AI. And I think setting yourselves up to be able to take advantage of that without being hamstrung by your own architecture, I think is a key takeaway that I'm taking forward. A few other lessons to carry forward. This one, number 2, may seem totally silly to even mention, but resilience is a major topic when it comes to electrification. And I would say that I did an interview of many central plant operators for a master's thesis, and every single one of them were basically technology agnostic. They just cared about having N+1, and design engineers do not always do that math correctly. So keep an eye out for that. 3 would be really leverage our growth. The fact that we're growing, sure, our absolute numbers are getting more challenging, but it's an opportunity for greater impact. The 4th thing I'd say is do everything you can to bundle decarbonization projects with energy efficiency to access financing. It can really help carry projects forward, including some of our heat recovery chiller projects. And ultimately, don't forget this is particularly for UC folks who have the 2045 goal, but really for anyone who has a goal far, far out in the future. I would say 40% greenhouse gas reduction now or in the immediate future is far more impactful from a climate change perspective than 90% in 20 years from now. So don't ignore the short game while you plan for the long. I know we have several questions, so I'll just leave this quote on the screen about the slowness of change, but still the importance of it while we review the Q&A.
And Thanks, Anna and Gabe. That was great, and I appreciate that wrap up and the lessons learned. And like you said, we do only have a couple minutes here, so I think if you're willing to maybe address some of those questions at your leisure throughout the day in the chat, that would be great. Because I know we're not going to have time, but I appreciate it. And maybe let's end on a high note. We hit a lot of challenges that you guys have seen. So we know what some of the hardest things are that you've encountered, but maybe what were some of the surprisingly pleasant surprises or easy things that you encountered as you went through your decarbonization journey? What were some of the things that maybe you expected to be hard that were easier, or support that you got from places that you didn't expect it, or any good news as you embarked on your decarbonization journey?
Yeah, I would say that two things come to mind. I don't think I would classify either one of them as easy, but positive for sure, was the fact that we have managed to bundle some pretty significant decarbonization projects into our energy efficiency financing. That energy efficiency financing is available to folks in the UC as long as your own capital folks will let it happen, and can manage to make the debt capacity work. But I see that as a major opportunity and a major win. We actually managed to influence the new hospital project in Parnassus with that financing availability to go the step forward and do the heat recovery chillers. They ended up not needing it in the end, but without that as a talking point and potential financing, it wouldn't have happened. And the second is I am incredibly pleasantly surprised that our Bayfront Medical Building with the super innovative heat recovery chiller and sink source coil design works. I think, as I said, major kudos to Gabe, the controls contractor, the commissioning agent, to actually make that work. But if anyone has detailed questions about how that's actually happening, we'd love to engage in that.